Okay, here's the big section. This is where everything that we've been working on for the past few weeks starts to come together into one. This is going to be the area of polygons. So the formula for the area of a polygon is going to be 1/2 ANS, or we could say 1/2 AP. Now, before we can start using that formula, we've got to figure out what are all the parts of a polygon. So here we've got the center of the polygon is obviously in the center. This is also the center of the circumscribed circle that goes around, and this is important, a regular polygon. So these are only going to be used on regular polygons, so polygons that have all the same angles and where all the sides are the same. Now, if we draw a line from the vertex of the sides to the center, these are going to be called radii, or the radius of the polygon. Why is it the radius of the polygon? Because it's the point, or it's the segment that goes from the center of the polygon, or the center of the circumscribed circle, to the vertex of the polygon, or the point where the polygon intersects the circumscribed circle. So again, this is going to be a radius, and if we have more than one, then we're going to call them radii. Now, here's another really important term that you need to know. The line that is drawn from the center to the midpoint of one of the sides at a perpendicular angle. So it's a perpendicular bisector. This line is going to be called the apothem. And when you look at the formula over here that says 1/2 ANS, this A is the apothem. Okay? Now the N stands for the number of sides. So you could have, if you've got a pentagon, you're using 5 sides. If you're using a hexagon, 6 sides, and on up. Then the S stands for the side length. So the side length is just the length of one of the sides of the polygon. The way that I'm going to teach you how to solve these is to take a polygon, and we're not going to worry about the entire thing. All we're going to worry about is one triangle that we create with the radii, and then one right triangle that we create with the apothem. Once you have done that, it actually becomes very simple to solve these by using either Pythagorean theorem or by using special right triangles, or in some cases you're going to have to use trig to be able to solve these problems. We'll move on with problem number 1. Before we move into finding the area of a polygon, we're going to look at breaking down the polygon a little bit more. So what we want to do is we want to find what are the angle measures of angles 1, 2, and 3. Now to do this, you have to determine what type of polygon do you have. And in this case, we're given a pentagon. So since we've got a pentagon, we've got 5 sides, which means that around this center point, we have 5 congruent angles, because in a regular polygon, all of these triangles that are created by the radii are going to be congruent triangles. Well, what you have to ask yourself in order to be able to find the measure of that central angle, we're going to call one of these a central angle right here. The measure of that central angle is going to be 360 divided by the number of sides. And again, the reason why we're going to do this is because when we go around that point, we end up with a circle. We have gone 360 degrees around that point. So that means we're doing 360 divided by 5. So 360 divided by 5 is going to give us 72. Right? So angle number 1 is equal to 72 degrees. That's going to make the second angle right here easier to find, because here's essentially what we're doing. We're taking a triangle that has a 72 degree measure here that we know is isosceles as well. And what we're going to do is we're going to draw a line straight through it. We're going to do an angle bisector that also is a perpendicular bisector of this side. So if this is an angle bisector, that means that 72 is split into 2 36-degree angles. So angle 2 is equal to 36 degrees. So now we have a 36-degree angle and a 90-degree angle there. So 126 degrees have been accounted for in this triangle. So remember that in a triangle you have 180 degrees. So 180 minus 126 is going to give you a 54-degree angle right there. So this angle where the radius and the side come together in a pentagon is going to be 54 degrees. Another way that you could have solved that is to have used the interior angle theorem. And you're looking for a single interior angle, so that means you could have used n minus 2 times 180 divided by 2. All right? And the way that this would have worked is this. We have a pentagon, so 5 minus 2 is 3, times 180 is 540. Divided by 5 rather. 540 divided by 5 would give you, let's see, 108. So you would have known that this angle here would have been 108 degrees. So if we're splitting that angle in half, then that means that that angle right there would be 54. So you can use either of those methods that you want. My personal preference, and the one that I'm going to be using in class all the time, is to go through this process here where I break everything down sequentially, as opposed to going to the interior angle measure and using that to break down what our angles are at where the vertices are. So in problem number 2, I'm going to show you how to go step by step and find all of the information that you're going to need for one of these polygons. In problem number 2, we're given that the figure that is a regular decagon. Now notice that I have not drawn a decagon over here. It's not necessary to actually draw the entire shape. All we're going to need to draw is one triangle, and then we'll split that triangle in half and work from there. So a regular decagon, we need to know how many sides does it have. So n stands for the number of sides. So a regular decagon is 10 sides. Then we need to know what is the central angle of a decagon. So the central angle is going to be equal to 360 divided by n. So since we've got 10 sides, that tells us that each central angle is going to be 36 degrees. So we're going to go ahead and write in 36 degrees there. Then let's go ahead and draw this triangle in now. And what this all means, this point right here, that is going to be the center of the decagon. Each of these vertices down here, that's going to be a vertex that is on the circumscribed circle. So we know that each of these are going to be radii, and these are going to be congruent to each other. Then we're going to draw in the apothem, and remember that the apothem is going to split this into 2 separate segments that are congruent to each other, and the apothem is going to be perpendicular to that side. With all that being said, if this entire angle measure is 36 degrees, then what is the angle measure of the bisected angle? The bisected angle is going to be 18 degrees. So we can put that in over here. Now, the next thing that we need to do is we need to find the perimeter, because we've already been given that the apothem is 12.3 and the side length is 8. So the perimeter is a really easy thing to find. All it is the number of sides times the side length. It's just the amount of distance around the polygon. So we've got 10 times 8 is going to give us 80 units. So whichever unit we're working with, centimeters or inches, whatever, it's going to be 80 units to the first power, because again, it's a measure of distance, not a measure of area. The next thing that we're going to find is the area without being put into a decimal. So we're going to put it into the simplest radical form or the simplest trig form that we can put it into. The second area is when we're going to plug it into our calculators and figure out what it is to the nearest tenth. So we want to do all of our areas to the nearest tenth. Okay? So in order to be able to do this, we need to figure out all of this information that's over here. 1/2 ANS, or 1/2 AP. Now, since we've already got the apothem is 12.3 and the perimeter is 80, we're actually good to go and use this particular formula right here. So we get A equals 1/2 times the apothem 12.3 times the perimeter 80. So what we end up with is half of 80 is 40, and so we get 123 times 4, and I'm going to go ahead and put that in because I don't want to mess it up. I have an idea of what it is. I think it's going to be 492, but want to make sure. 492. So we get the area is going to be 492 units squared. Now this one was not too terribly difficult because you can see that we didn't have any radicals to work with, we didn't have any trig to work with. So we got our solution fairly quickly. It's not always going to be this clean, and we're not always going to leave this one blank. So understand that there are going to be times when we have to find what the measure of the apothem is, or we have to find what the measure of the side is. And that's when we're going to bring in our trig or our special right triangles, and that's going to make the process a little bit more complicated. More complicated like in problem number 3. So in this one we're given a hexagon. So let's go ahead and fill in our number of sides for a hexagon, which is going to be 6. The next thing that we need to do is we need to figure out what is that central angle of a hexagon. Remember, we're going to use the formula 360 divided by n to find that central angle. So we get 360 divided by 6 gives us a 60-degree measure. So we know that this central angle here is going to be 60 degrees. We can then very easily figure out the bisected angle by saying 60 divided by 2 is 30 degrees. So what you should notice here is you now have a 30 and a 90, which means that this is a 60 down here. So we have a 30, 60, 90 right triangle. That means we're going to be using special right triangles to solve this problem. In this case, we need to find the apothem, and we also need to find the perimeter. Now the perimeter is going to be pretty simple. We already know that the side length is 3. We know that there are 6 sides in a hexagon, so that means that our perimeter is going to be 18 units in length. We still have to find this apothem though. So what we want to do is this. We want to say, since we know that this segment is congruent to this segment, what is the length of the segment? It's going to be 3/2, or 1.5. I'm going to use 3/2 because usually using fractions is going to be much easier than using decimals on these. So now I need to figure out, what does this 3/2 represent in my a square root of 3, 2a relationship? Well, this is across from the 30-degree angle. So that means that a is equal to 3/2, which tells me that the apothem, which is across from the 60, is going to be 3/2 square root of 3. So I'm going to come in over here and write in 3/2. Wrote that a little bit too big, so reduce the size of that. 3/2 square root of 3. Once I have that, I can start looking for the area because I have the perimeter and I have the apothem. I have enough information to go into my formula. So A equals 1/2 times the apothem, 3/2 square root of 3 times the perimeter, 18. So now let's go ahead and take care of these fractions first. 1 times 3 is 3, 2 times 2 is 4. So we get 3/4 square root of 3 times 18. Now, what I'm going to do is 3/4 times 18. Is there anything that I can do in order to cross reduce? There is. 2 goes into 4 twice, and 2 goes into 18 9 times. So 3 times 9 is 27. So we get 27/2 square root of 3. That is going to be our area in terms of our radical. So 27 over 2 square root of 3 units squared. Now the second area is when we take out our calculator and we plug in the final solution that we got, the simplest solution that we got. That way we make sure that we get the most accurate decimal that we can get. Because remember, it's going to be an approximation. And anytime that you're using an approximation, you cannot be using an approximation early on in the process, because that means that the final answer is going to get further and further away from the actual true answer. So we do 13.5 times the square root of 3, and that is going to give us 23.38, or approximately 23.4 units squared. So that is how you're going to use special right triangles. Now there are going to be a couple of different types of polygons that you're going to use special right triangles on. The hexagon is going to be one of them, and you'll see some of the other ones you're going to use that on a little bit later. Okay, we're going to do one more extra problem that's not in the book, just to make sure that you understand how to use trig when we're doing these problems. So in our extra problem, we're given that we've got an octagon with a radius of 4. So you can see that I've got my triangle shape that represents one of the 8 slices of this octagon. And I've labeled this radius as 4. But in order to be able to solve this problem, you have to have an apothem and you have to have a side length. So we've got to figure out what are the apothem and side length on this problem. So the first thing we're going to do is fill in our number. Since it's an octagon, we know that an octagon has 8 sides. Then the central angle of an octagon is going to be 360 divided by 8. So that gives us 45 degrees. So we know that this angle right here is going to be a 45-degree angle. So when we bisect it with the apothem, that gives us a 22.5-degree angle. So we know we've got 22.5 there. Now we've got to see if we can figure out what is the length of this apothem. So to be able to do that, we're going to have to use trig. In this case, we have this angle right here that has been identified on this right triangle. So since we've got an angle on this right triangle that we know, and we've got a side length that we know, we can go ahead and use trig. So we've got this angle, we're looking for this side right here. So this is the adjacent side, or the adjacent leg. And we're given the hypotenuse. So adjacent and hypotenuse tells us cosine. So we're going to do the cosine of 22.5 is equal to A over 4. Because the apothem is the adjacent, and then the 4 is the radius. So that gives us then 4 cosine of 22.5 is equal to the apothem. So I'm going to write that in right here. Now I do not want to calculate out 4 cosine of 22.5, because if I do that, I'm going to end up with an approximation. And I'm going to end up with an approximation here. So when I go to multiply 2 approximations together, it's going to make the final approximation that much further off of what it should be. So leave this as 4 cosine of 22.5. And I'm going to go ahead and write that in here as well. Now I need to find this side right here. But remember that I'm only taking half of the side of the octagon. I need to then multiply whatever this solution is right here by 2 in order to get the full side length. So I need to figure first out what is this half of the side going to be. So I'm looking at the opposite from 22.5 and the hypotenuse. So opposite and the hypotenuse tells me that I'm looking at sine. So it's going to be the sine of 22.5 is equal to the side over 4. Now remember that I'm going to have to multiply this entire thing by 2 anyways, so I'm going to put a 2 out here in front of 2 sine of 22.5. So when I multiply this by 4, I get 8 sine of 22.5 is equal to the side. So 8 sine of 22.5. If you did this correctly, here's how this should work. If you're dealing with sines and cosines, then the side should have a number that is twice, basically like these are coefficients. The coefficient on the side should be twice what the coefficient was on the apothem, and if you're using the same angles. So now I have enough information here to be able to figure out what the perimeter is. So the perimeter, remember, is going to be the number of sides times the side length. So it's 8 times 8 sine of 22.5, which is going to be 64 sine of 22.5. Once I have that, I can then fill in my formula, or basically what my formula is for A1. So I've got to do 1/2 AP. So A equals 1/2 times the apothem. And I'm going to need more room, so I'm going to erase this. So 1/2 times the apothem, which is 4 cosine of 22.5, times the perimeter, which is 64 sine of 22.5. Then I can combine this together. 1/2 of 4 is 2. So I get for this, area 1, this is the actual, so I'm going to put equals on this. 2 cosine of 22.5 times 64 sine of 22.5. I could actually take this even further down and multiply this 2 and this 64 together. And what that's going to give me is going to be 128 cosine of 22.5 sine of 22.5. This is the most accurate answer possible because nothing has been done to approximate yet. So now I'm going to take this into the calculator and go 128 times the cosine of 22.5 times the sine of 22.5, and that's going to give me 45.25, so approximately 45.3 units squared. And I'll put units squared over here as well. And you can see this is how you're going to work out a problem in which you have trig involved.